Okay, this is section 3.5, which is empirical and molecular formulas from combustion analysis, and we're going to be going through that today. So starting off with what is combustion? Combustion is reactions where oxygen combines with a substance, commonly a hydrocarbon or some sort of organic um, solution to produce carbon dioxide, water, and release heat and light. So here in this example here, we have methane combining with 2 oxygen to create carbon dioxide and 2 water. So this balanced equation just basically shows how combustion reactions work, and obviously not shown in this reaction, but heat and light energy are released from this. Okay, so moving on now to what is an empirical formula. So the empirical formula is simply an equation that shows the amount of moles in the simplest form within each compound. So that's basically saying the number of atoms relative to each other. So if you have a formula like C2H6, you simplify it down to CH3. It's the same ratio of atoms within the compound, so it doesn't matter. There's a mole of carbon and in 3 moles of hydrogen, and it's that same 1:3 ratio as it is in C2H6. So it's just simplifying that to get the number of atoms relative to each other. Okay, so we're going to go through a problem of how to calculate an empirical formula. So like I said, it's just to obtain the lowest whole number ratio of elements within that compound. So we're going to go ahead and go through this first problem. So combustion analysis of toluene, a common organic solvent, gives 5.86 milligrams of carbon dioxide and 1.37 milligrams of water. If the compound contains only carbon and hydrogen, what is its empirical formula? Okay, so first we're going to start off with what we have. We have 5.86 milligrams of carbon dioxide. We're going to take that carbon dioxide and convert it into grams. There's 1,000 milligrams in a gram, so you convert it here. Once that's converted, you're converting grams into moles so that when we get with moles, we can work with ratios, and that makes it a lot easier. So 1 mole is equal to 44.01 grams of carbon dioxide, which is just given from the fact that carbon dioxide is 12 atomic mass units and oxygen is 16. And then the ratio is just there's 1 mole of carbon within the carbon dioxide because there's no subscript on it. So that gives us 0.00013 moles of carbon. So then we go ahead and we do the same thing for hydrogen, and we have 1.37 milligrams of H2O. We do the same thing where we convert milligrams into grams, and then we go ahead and we convert grams into moles again. And the difference with this one is there is 2 hydrogen within H2O, so it is 2 moles of hydrogen over 1 mole of H2O. And that will give us 0.00015 moles of hydrogen. So we have taken our milligrams, which we were given, and we have converted them into moles so that they can work with each other and we can work to get our formula. So next, we're going to take those moles that we have and divide them by the smallest amount of moles that we calculated. So obviously, 0.00013 is less than 0.00014, so we're dividing both of them by the moles of carbon. And this will give us our smallest ratio, because this will turn into 1 and this will turn into 1.14. So we have a 1.114 ratio. Now, I don't know if you remember, but it's the smallest whole number ratio. So what we have to do then is multiply it by the smallest number possible in order to maintain the ratio. So if you go ahead and multiply it by 7, you get 7 moles of carbon and approximately 8 moles of hydrogen to give us the empirical formula of C7H8. So that's an example of how you calculate empirical formula when you're given your carbon dioxide and your water, and it says that it's a combustion reaction. So next, we're going to move on to a molecular formula. So a molecular formula is a formula giving the number of atoms of each of the elements present in one molecule of a specific compound. It's basically a modification of the empirical formula so it matches the given molecular weight of the substance. And I'll go more on that later. So going back to the same example we had before, C2H6 is an example of a molecular formula because it matches the molecular weight of this compound. It is not simplified. Now sometimes the simplest form, in this case, we're going to say that the molecular weight is 30 atomic mass units. So this is the molecular formula because it matches 30 atomic mass units. Now, the way you get this is you take your empirical formula, which is equal to 15 mass units, because this is 12 plus 3, because the weight of this is 1 times 3, 3 times 12, 15. So if you are given that it's 30 atomic mass units, you then have to multiply this by 2 to get C2H6, giving you the molecular formula. The ratio is still the same, but the mass is different because it's a different amount, and you need it to match the given molecular weight in the problem. And I'll give an example on this. So here we go. We're going to calculate our molecular formula now. So we're going to use our same empirical formula of toluene, and we're just going to say that the molecular weight is 276 atomic mass units. Now this is not true, but for the sake of this problem, we're saying it's 276 so that it's easier to work towards and we don't have to do more work than we need. So like I discussed before, the weight of carbon is 12.011 atomic mass units, and the weight of hydrogen is 1.00794 atomic mass units. But for the sake of this example, we're just going to simplify it to 12 and 1. All right, so first we're going to go ahead and we're going to multiply 7 times 12, because there's 7 carbons, and 8 times 1, because there's 8 hydrogens, to get us 92 atomic mass units from here. Now, we need to get to 276 atomic mass units. So right here, we have 276 divided by 92, which is equal to 3. So in order to get our molecular formula, we have to multiply our entire equation by 3 so that the molecular weight matches the weight that we calculate. So we multiply that by 3 and we get our molecular formula of C21H24. It's as simple as that. You're going to calculate the weight in the empirical formula, and if it doesn't match the molecular weight that you are given, you're going to apply, sometimes it's times 2, sometimes it's times 3, times 5, sometimes it is equal. For the case of actual toluene, it is 92 atomic mass units. So in that case, this is the empirical and the molecular. All right, now we're going to have you try one on your own. Menthol. The substance we can smell in methylated cough drops is composed of CHNO. A 0.1005 gram sample of menthol is combusted, producing a 0.2829 grams of carbon dioxide and 0.1159 grams of H2O. What is the empirical formula for menthol? And if menthol has a molar mass of 156 grams per mole, what is its molecular formula? So pause the video here and solve it, and I'll go through how to solve it after that. So first, we're going to take what we have, just like before, 0.2829 grams of CO2. We're going to do the same thing as before and convert it into moles, right? I'm not going to explain that again. So then, because we are given the grams and we have of the entire thing and we don't know how much oxygen is within, we're going to then convert this moles also into grams of carbon so that we can use that later. Now we are going to go ahead and do the same thing for hydrogen. We're going to take our 0.1159 grams of H2O and convert that into moles of hydrogen. And just like the carbon, we're going to convert that also into grams to use for later. And we're going to go ahead and we're going to use that, and we're going to go 0.1005 grams of menthol minus the grams of carbon minus the grams of hydrogen is going to give us the grams of oxygen. So that was our unknown, and now we can use that to solve for the moles of oxygen. So we take our grams of oxygen and we divide it by 16 because that is the atomic mass of oxygen. And that's going to give us 0.00065 moles of oxygen. Now, that is our smallest number. So you know what we're going to do next. We're going to go ahead and we're going to divide all of our moles by the smallest amount of moles, which is oxygen. And that gives us 10 moles of carbon, 20 moles of hydrogen, and 1 mole of oxygen, which gives us the empirical formula of C10H20O. And the molecular formula is also going to be C10H20O. Now, if you're wondering how the empirical formula is equal to the molecular formula, remember that I said before, when the given molar mass, 156 grams right here, is equal to the mass of the empirical formula, there's no change you need to do to the molecular formula. So if you add it up, 10 times 12 plus 20 plus 16 is equal to 156. So right here, our formula weight of the empirical formula is equal to the given molar weight. So there's no change we need to do to the molecular formula. That's all that I have for 3.5, empirical and molecular formulas with combustion, and hope you guys learned something.